brown, black, orange, gray, green, or blue. Over the billions of years that came before us, our planet has been every color imaginable. Relying on the latest discoveries, we will dive into the fascinating history of the early Earth, flying over the surreal landscapes it gave birth to. Our adventure begins as far back as we can go, 4,530,000,000 years ago, in a period called AD1. We are about 100 million years after the birth of the solar system, and our planet has just completed its formation. There is no paradise on Earth then, everything is nothing but a real hell. The entire surface, as well as the depths, are completely molten, and the world is covered by a global ocean of incandescent lava, whose constant bubbling is maintained by the energy released by radioactive materials, abundant in the primitive solar system, which have slowly sunk to the center of the Earth and heat it from within. But also by repeated collisions with meteorites and comets, which frequently strike the planet. Despite all this, the violence of these impacts is nothing compared to the truly cataclysmic collision that our planet experienced a few million years earlier, when it crashed, in an end-of-the-world screech, into a planetary embryo the size of Mars. Under the incredible violence of the impact, hundreds of thousands of cubic kilometers of molten rock and metals were thrown into space, where they formed a vast ring of molten debris. And while some of the white-hot elements from this disk of debris in orbit fell back to Earth, the rest clumped together to form our satellite in just a few 100,000 years. Above this global ocean of magma, the moon is still a glowing ball, 20 times closer to us than it is today. From the ground, it appears visually enormous and takes up an unreasonable fraction of the sky. The proximity of our satellite, which at that time completes an orbit around our world in less than 3 days, coupled with the rapid rotation of our planet, which completes a turn on itself in just a few hours, this generates powerful tidal effects that deform the ocean of viscous magma. As a result, Earth becomes the stage for lava tides, which periodically create a bulge several kilometers high. Because of the phenomenal amount of accumulated energy, this global magma ocean will persist on the surface for several 100,000 years before the ground begins to solidify in some places. The slightest piece of crust that forms on the surface of this infernal cauldron is as fragile as it is short-lived, because convective currents rising from deep below regularly recycle and dissolve those solidified regions. The solidified regions, which are like immense rafts of rock on an ocean of glowing magma, slowly cooling down. At the same time, this apocalyptic scene of lava and light was covered by a heavy and scorching atmosphere, fueled by gases that, initially dissolved in the molten rocks, escape when those rocks solidify. This massive degassing from the planet's glowing interior fills the atmosphere with steam, scorching water, CO2 nitrogen, carbon monoxide, dihydrogen, methane, and other sulfur compounds, which envelop the world in a thick layer of clouds. Seen from space, the Earth is then covered by a dark and opaque veil, probably gray, brown, or copper-colored, behind which the glowing surface appears only intermittently, like embers seen through a thick fog. Assuming it was possible to survive on the surface, to walk here, you would feel less like you were moving through air and more like you were moving through a burning fluid that is as dense as it is sticky. Because the staggering amount of water vapor suspended in the atmosphere exerts a pressure probably tens to hundreds of times greater than what we know today. In this turbulent atmosphere, particles charged with static electricity, which are continuously spewed out by eruptions and nascent volcanoes, encourage the formation of lightning. So the sky crackles with an almost constant background noise of thunder. Subtitles: on the horizon, twilight is almost constant. Because under this sky that never really opens up, the light of the young sun, which is about 30 times less bright than today, barely penetrates and diffuses through the clouds. And less than 1% of the incoming radiation reaches the surface. Surprisingly, even though the sun is less powerful than it is today, the planet's cooling process is relatively slow. because the thick greenhouse gas-rich atmosphere acts like a thermal lid that traps heat. The early Earth is, in a way, a planet under a bell jar, where only a small portion of the energy emitted by the lava escapes into space, while the majority remains trapped by a monstrous greenhouse effect. For about 20 million years, water exists here only in the form of vapor. As the temperature continues to slowly drop, the planet's surface becomes increasingly covered with solid crusts. Riddled with volcanic faults, it looks like the skin of a dragon in the process of healing. And when the surface temperature drops below 373 degrees, water leaves its critical phase. And under a sky nearly 200 times heavier than today's, it begins to condense. Then the planet abruptly shifts to a new state. For thousands of years, torrential rains lash the entire Earth. And the water that keeps falling from the sky gradually begins to fill the first oceans. Oceans whose temperature is initially several hundred degrees and which are kept in a liquid state by the tremendous pressure exerted on them by the atmosphere, like the lid of a pressure cooker. When the temperature drops below 300 degrees on the surface, the oceans are already nearly 2 kilometers deep. And as the atmosphere continues to lose its water vapor, the escape of radiation into space becomes much more efficient, and the cooling of the Earth accelerates. At the end of this deluge, almost the entire planet is covered by a single ocean, with only a few rare, fleeting volcanic landforms rising above it. These dark surfaces, streaked with glowing red fractures, are regularly reclaimed and swallowed by rising magma, but also eroded by the violent movements of the ocean. Because of the moon's proximity, tidal forces at this time are hundreds of times stronger than what we know today, causing the local water level to fluctuate by nearly 100 meters several times a day. The Earth completes a rotation in just about 10 hours, and the tidal cycles follow one another at a frantic pace. Here, the surface rocks are also continuously leached by highly acidic rain and by the hot, corrosive waters of the first oceans, which, as they become loaded with dissolved minerals that absorb light, take on dark hues. If you had sharp eyes to see beneath the clouds, you would notice that on the horizon there are still no mountain ranges and no real continents. Here, only the volcanoes that line up along gigantic faults temporarily break through the single ocean. And millions of years, like lava, continue to flow by, and the Earth has once again slightly changed its face. The thick atmospheric veil that surrounds it now, in some places, reveals vast emerging continental expanses, built by volcanic activity, which is still extremely intense. Despite all this, the persistence of solid ground on Earth remains an exception. The exposed land then covers only a few % of the planet, and these landforms that temporarily break through the ocean are fragmented and unstable. Almost all of them are eroded or recycled in just a few million years. Even though the planet is no longer a continuous inferno, and the atmosphere can clear up in some places, everywhere lava comes into contact with the ocean. Plumes of water vapor form and rise into the sky, giving birth to thick, almost permanent clouds. The atmosphere, however, remains terribly corrosive, and the sky, always filled with volcanic particles, diffuses the sunlight that struggles to make its way down to the surface, and bathes the landscapes in a milky light with shades of yellow, brown, and rust. If by magic you were teleported here, death would be almost immediate, because the air, saturated with CO2 and nitrogen, is devoid of oxygen and therefore unbreathable. Yet, strangely, this inhospitable environment is extraordinarily productive. Because the sun's radiation continually tears apart the methane molecules, probably present in abundance in the atmosphere, triggering chains of complex chemical reactions that give rise to large quantities of volatile organic compounds. The radiation from the young sun also promotes the formation of aerosols. These volatile particles, which serve as condensation nuclei, promote the formation of clouds that take on the appearance of organic or sulfurous hazes. So it is likely that our blue planet had an orange appearance at that time, as seen from space. On this Earth, still dominated by the colossal flows of heat rising from the planet's depths, the landscapes are beginning to show contrast. Some regions are experiencing phases of extreme volcanism, while others, more temperate, are enjoying a relative calm. In these ancient times, the oceans not only cover the vast majority of the planet, they also penetrate its crust, which are constantly weakened and fractured by internal heat, tidal effects, and meteorite impacts. Thus, at the bottom of the oceans, water seeps into the depths of the crust. Then, after being pressurized and reaching temperatures of several hundred degrees, it rises back up loaded with dissolved metals, giving rise to vents, to hydrothermal systems. Today, these formations are concentrated on our planet along the 60,000 kilometers of mid-ocean ridges, which are only active in certain sections. So, in total, there are only a few hundred major sites across the entire Earth. But during the Hadean, the heat flow of our planet was much higher than today, and the ocean floor was rich with hundreds of thousands of hydrothermal cells active at the same time. Through these open wounds, phenomenal amounts of water circulate constantly. The most reasonable estimates suggest that during the AD1, the flow rate of all these hydrothermal systems, spewing out boiling water, was rising from the depths at a frantic pace, was such that a volume equivalent to that of all the planet's oceans passed through the Earth's crust in just tens to hundreds of thousands of years. And it was in this setting of a still feverish world, 4 billion years ago, that the Aeon arc began. We are entering the period in Earth's history from which intact rocks have reached us. Volcanic activity remains intense, about 5 times higher than in recent times. And strange, ultra-fluid lavas called komatiites regularly flow onto the surface, drowning entire regions under hundreds of meters of magma. Despite everything, some portions of the Earth's crust escape total remelting. We have entered a geological era in which the Earth begins to preserve its records. At the beginning of the Aeon arc, the danger comes less from the Earth's depths than from the sky. Because Jupiter's migration along its orbit destabilized the asteroid reservoirs located at the edge of the solar system, and many of these frozen bodies then come in irregular waves to crash onto Earth. Major impacts did not spare our planet at all during the hundreds of millions of years that AD1 lasted, but their frequency then rises dramatically. And for nearly 300 million years, our planet underwent intensive and intermittent bombardment. Because the assaults from rocky and metallic meteorites, as well as comets crossing Earth's orbit, do not resemble a permanent curtain of fire, but rather an alternation of calm phases and sudden catastrophes. So, on average, an impact of more than 10 kilometers in diameter strikes the surface every 10 million years. With each major impact, there is absolute annihilation locally. Where the body crashes in a fraction of a second, the crust is instantly vaporized and melted around the point of impact, and the oceans start to boil for hundreds of kilometers around. But each time, Earth doesn't undergo total sterilization, and above all, the world doesn't start over from scratch. Because these impactors are not just destroyers, they are also carriers, delivering water, metals, and carbon compounds. In the end, during the first 700 million years of Earth's existence, the ice contained in the comets that crashed here helped increase the amount of water on the surface by nearly 10 times. Enough to raise the level of the planet's oceans by several hundred meters. Seen from space, the Earth now probably looks like a raging sea of cotton, covered with thick turbulent clouds whose formation is fueled by the intense evaporation of the oceans. Because the atmosphere, which remains rich in CO2 and especially in water vapor, still maintains a strong greenhouse effect, and the temperature of the air and the water fluctuates between 40 and 80 degrees. For millions of years, gigantic storms and ancient cyclones rage and sweep across the globe almost without respite. Fueled by the high rotational speed of the Earth, which completes a full turn on its axis in just 13 hours. The presence of this cloud-filled sky, rich in greenhouse gases, is a good thing. Because without this veil, the planet would freeze. Because the sun, still young, only has about 80% of its current brightness. If you were teleported to these shores, at first glance this strange world would seem barren to you. Yet, on a microscopic scale, something has come to life. In the oceans that lap against this bare mineral landscape, life is already beginning to emerge. And in these warm waters, in some places, archaea drift about, feeding on ferrous ions from which they draw their energy. The presence of these unicellular nucleus-free beings, which are perfectly adapted to a world still devoid of oxygen. And they thrive in waters with high salinity, and whose acidity would make you regret being born, reminding us that life did not begin in a peaceful garden. 200 million years later, the global ocean no longer stretches as far as the eye can see, because the amount of land above water has increased considerably. And here and there, we find the first proto-continents that formed along volcanic arcs. Although the tides have calmed slightly, due to the moon's continued distancing, the shores of the primitive continents are still subject to periodic changes in water levels, with amplitudes that can still reach dozens of meters in some places. Because in the sky, our satellite is still 3 times larger than it is today. The waters of the oceans from that time probably took on dark and greenish hues. Because without oxygen to make it precipitate, the iron remains dissolved in a soluble form, at concentrations that can be hundreds to thousands of times higher than those of today's seas. The oceans are then giant metallic solutions, practically opaque, in which the dissolved iron changes the optical properties of the water, which, under a yellowish gray and orange sky, absorbs almost all colors, reflecting only green. But gradually, in the atmosphere, something begins to change imperceptibly. Because on the shores of these primitive oceans, we find microbial mats organized into colonies. Cyanobacteria, which together form strange structures, deposits of fossil carbonate that are called stromatolites. By inventing photosynthesis, using the energy of the sun, water, and carbon dioxide from the air to produce sugar while releasing oxygen, these seemingly insignificant forms of life will, over a long period of time, have an influence on the scale of the entire planet. Life ceases to be just a discrete passenger. It becomes a geological force capable of transforming the world to the point of giving it new faces. These changes are subtle at first. For hundreds of millions of years, the small amount of oxygen produced by the activity of these unicellular living beings struggles to accumulate in the atmosphere, because it dissolves in the seas, where it reacts almost instantly with the iron in solution, which it oxidizes and slowly precipitates. This marks the arrival of blue, as the oceans slowly lose their metals, become clearer, and shed their greenish tint. And the light that penetrates them more deeply begins to give them the color we know them for. Then, about 2 to 2.5 billion years ago, the amounts of oxygen released by these microscopic organisms reached such concentrations that all the dissolved iron in the seas precipitated to the bottom of the oceans, thus creating gigantic deposits of rust. It's likely that you currently have objects at home that were formed thanks to the activity of these primitive life forms. Because 90% of the iron ore mined in the world today comes from geological formations dating back to those times. It is believed that the Great Oxidation Event played a central role in repeatedly triggering total glacial periods on a colossal scale, traces of which can be found in the rocks that have come down to us from that era. During these so-called Huronian glaciation phases, the average global temperature dropped drastically to the point where almost the entire surface of the oceans began to freeze. The arrival of these white desolate landscapes, which would remain in place for about 300 million years, is probably indirectly linked to the release of oxygen by living organisms. because this element reacts with the methane present in the atmosphere and, by destroying it, causes the concentrations of this powerful greenhouse gas to drop, and with them, the temperatures. While traces of this snowball Earth phenomenon have been partially found, the process that allows the planet to emerge from it is still unknown. Perhaps it's the volcanoes. Let's take another leap in time. 1,850,000,000 years ago, oxygen concentrations in the atmosphere reached levels high enough to oxidize the iron-rich rocks of the emerging lands, which in turn literally began to rust. As a result, the landscapes on the surface took on an orange hue for millions of years. By attacking minerals and binding to them, oxygen helped their number explode, increasing from 2,500 to about 4,500 different varieties under its corrosive action. In other words, nearly half of the types of minerals found on Earth today owe their existence to the arrival of oxygen. At the same time, this oxygen helps form the ozone layer, which is a byproduct of it and filters out high-energy ultraviolet rays. The arrival of this layer will later allow living beings to venture out into the open air. With the arrival of oxygen in the water and then in the atmosphere, organisms capable of breathing it and using it to produce energy will gradually outcompete those that rely on fermentation. And while the surface of the continents keeps rusting, the air itself becomes clearer. During the previous 2 to 2.5 billion years, the Earth has seen all kinds of things. But at no time were the skies blue. Because in the absence of ozone, the power of ultraviolet radiation continuously produced molecules that formed thick hazes. Thus, the activity of microscopic living beings literally managed to change the face and the colors of the world. Sometimes evolution is a revolution without looking like one. And it is beneath these landscapes, which are beginning to look like the ones we know, that our journey to discover the primitive lands comes to an end. As the very first plants begin to colonize dry land about 500 million years ago. Now, the question you may be asking is, how did we know all this? And what is new in this story? How have these visions of our planet's past evolved in light of the latest discoveries? If you were attentive at school, or if you have watched a lot of documentaries about the history of the Earth, you have surely heard this story told many times through two very distinct main acts. On one side there's the Hadean, an era depicted as a kind of permanent hell. A long planetary nightmare dominated by heat, eruptions and impacts, often presented as sterile and unlivable because it was too violent to be habitable. And then, on the other side, the Archean, the time of origins, when the Earth, finally calmed, would have cooled and stabilized enough to sustain liquid water, continents, and eventually life. And then, between these two great acts, a clear boundary was often drawn, marked by the late heavy bombardment, whose meteorite and comet impacts supposedly brought most of the water found on Earth today. Except that the discoveries made over the past decades, which we have outlined for you, have come to transform this view. This scenario of a world trapped in hell has been replaced by the vision of a planet that didn't wait for the end of violence to become chemically interesting. Today, we actually believe that the oceans formed extremely quickly, and that most of the water found there was already present from the beginning. Studying the Hadean period is extremely difficult because the surface of our planet was constantly being reshaped. Yet, even though the Earth has erased almost all traces of that era, tiny but incredibly telling witnesses from those distant times have reached us. These witnesses are the zircons. These crystals, often smaller than a grain of sand, are extraordinarily robust, to the point of being able to remain intact for billions of years. In the rocks where they formed, even when those rocks have been crushed, buried, and remelted, by studying the atoms that make up the crystal lattices of these zircons, researchers have black boxes that allow them, indirectly, to see the early Earth. This is how crystals of zircon over 4 to 4.3 billion years old were discovered in rocks. whose composition shows that they formed by interacting with liquid water, which made it possible to prove the presence of oceans on our planet just 100 million years after its formation. It should be noted that the existence of these zircons indicates the presence of liquid water, but not necessarily on the surface. Since water has the particularity of freezing from the top, these zircons could very well have formed on an Earth entirely covered with ice, beneath which there was a liquid ocean. The sulfur atoms they contain, which have reached us from that period, preserve the trace of reactions, which can only take place in a thick atmosphere, extremely poor in oxygen, and exposed to intense ultraviolet radiation. As for the iron atoms that were deposited during the Archean and that we find today in immense deposits, they are witnesses to a world where the metal was mobile, reactive, and omnipresent before being precipitated by the arrival of oxygen. The second recent discovery that led us to shake up the history of the early Earth concerns our view of the late heavy bombardment. It's important to understand that to study the periods of our planet's history that are the most distant from us in time, one trick is to look into the history of our satellite. Because the Moon, unlike our planet, has preserved its records almost intact. On Earth, erosion, volcanism, and the movement of tectonic plates have erased almost all traces of that era. But the Moon is a dead celestial body, without an atmosphere, without volcanoes or oceans to dissolve or erode, so its scars are preserved over time. The lunar surface is therefore a record of accumulated impacts, some of which date back to the first hundreds of millions of years of the solar system's existence. By studying and dating the large impact basins of our satellite, we are not only measuring the age of a collision, we are also constraining the rate of violent events experienced by the entire inner solar system. For a long time, it was believed that the study of rocks brought back from lunar craters provided evidence of a period when a rain of asteroids and comets ravaged the surface of our planet, bringing with them large quantities of water trapped inside these celestial bodies. Except that the increasingly detailed understanding of the dynamics of the solar system and advances in technology that have allowed for more precise dating of lunar rock samples have recently undermined the spectacular scenario of the late heavy bombardment, by showing that this deluge from the sky contributed less to enriching the oceans than we originally thought. And above all, that this deluge was much more spread out and spaced over time than we initially thought. At the same time, the study of the nature of the water contained in comets and asteroids, which space probes have analyzed, has finally convinced us that the vast majority of the water that is now on our planet was already present in the mixture of molten rocks that gave birth to our world, and that the oceans are therefore essentially the result of the intense degassing of the primitive Earth. All these combined discoveries mean that the history of our planet as we understand it today looks less like a clear break between hell and habitability, than to a long transition marked by a global decrease in internal energy, punctuated by extreme events where life did not wait for everything to be perfect to try its luck and emerge. And then, there is an indirect proof of the existence of these environments that I personally find absolutely fascinating, because it is not written in the rocks, but in us. Indeed, the compositions of the environments of the past that we just talked about are indirectly confirmed to us through the way life works, because all living beings retain within them, in their molecular machinery, a memory of those ancient times. The unique chemistry of these environments has indeed left traces, kinds of functional fossils, that can be found inscribed in the architecture of the molecules that make us up. Thus, when we look at the most fundamental reactions that take place at the heart of the cells of every living being, we observe the presence of many biochemical circuits whose development only makes sense in environments different from those of today's Earth. Oxygen-sensitive enzymes, for example, which are found at the heart of many fundamental metabolisms, are functional relics of a world where this molecule was a rare poison and not a resource. The first versions of these enzymes appeared during the Archean era, when oxygen was still almost absent. And when this molecule later spread, it tinkered with the innovations that had already been developed and created molecular protection systems, such as antioxidant enzymes, to cope with its presence. but the core of metabolism itself remained. So much so that life forms still mainly use anaerobic metabolic pathways at the heart of these energy networks, even though we live in an oxygen-rich world. Similarly, the fact that many key enzymes in living beings use iron and sulfur at the core of their processes reflects the availability of these elements in the oceans where they originated. On present-day Earth, these choices are not optimal. They appeared in a world where water was rich in dissolved iron and free oxygen was absent. In short, where the rocks have been erased, the functions have survived. And we carry, inscribed in the very structure of the matter that makes us up, the constraints imposed by these vanished landscapes. Beyond being a treat for the mind, learning more about the conditions on the early Earth lets us begin to approach the mystery of life's emergence, and to try to understand how it managed to emerge so quickly in environments that would make you instantly regret being born if you so much as dipped a toe in them. Despite all these recent exciting discoveries, the greatest mystery remains opaque. We still don't know exactly when and how life emerged. In the meantime, remember that to get away from it all, it's not always necessary to imagine parallel worlds. Sometimes, all it takes is to sit down and wonder what this place looked like several billion years ago. And even if none of these landscapes have ever been seen by a human being, thanks to science, we've been able to give them names and anchor them in our imagination. And in our minds, the past has become a great number of other planets. But stay with us. We'll chat with Frank, the researcher who helped write this episode. Frank, hello, and thank you again for helping me write this episode. Today, we followed a scenario that's consistent with what we know and that we could sum up as: the atmosphere was rich in greenhouse gases and the Earth was relatively warm. And there are also alternatives to this scenario. You've explored these questions for a long time, and I believe your thesis focused on the early Earth's atmospheric composition. Could you tell us a bit about the other possible trajectories or scenarios and why, well, it's complicated to have a perfectly clear vision? Yes.
It's complicated. It's even very frustrating. We would really love to have a time machine. So the further back in time we go, the fewer solid constraints we have on what was happening on Earth. Of course, when it comes to life, we have fewer and fewer fossils, fewer fossil traces. So we don't know exactly when life appeared. And for the atmosphere, it's the same. We have very few constraints. We have one fairly reliable constraint, which is the moment when oxygen becomes a major component of the atmosphere. Major, at least in terms of its chemical role. That was 2 to 2.5 billion years ago, or 2 to 2.3 billion years ago. We shift from an atmosphere that is basically without oxygen, without any chemical effect from oxygen, to an atmosphere that will begin to leave its mark. All the geological traces of its action. And it's really a very important shift for, mineralogy, but also for living things. And if we go even further back in time, well, yeah, we go more and more into the unknown with fewer and fewer constraints. So if we go back to the beginning, close to the formation of the Earth there, our evidence, well, it's the meteorites. It's actually more about the other bodies in the solar system than the Earth itself, which is kind of left out. So we have models. Basically, we start with an Earth made up of very hot meteoritic material, and then we let it cool down. And as it cools down, well, it releases its atmosphere because it has accreted its gases in the form of rocks. You see, it didn't accrete them from the surrounding gas like Jupiter or Saturn did, because Earth took a long time to form. So it's no longer in a gas disk by the time it forms. So it releases gas as it cools down because solid rocks contain much less gas than liquid rocks. So it expels that gas, and little by little an atmosphere is created. And so in the idea we have, it's more of an atmosphere made of water vapor at first, carbon dioxide, but probably also other components. We don't know. It's not very clear yet. And the distance at which the Earth is from the Sun is a bit critical. That, and also the evolution of the Sun. Because actually, if the Sun had from its formation the luminosity it has today, it was weaker, much weaker. it only had 70% of its luminosity. Well, the atmospheric water vapor wouldn't have been able to condense into an ocean. That means that today, if we vaporize the Earth's oceans, they would create such a gas, such a greenhouse effect, that they couldn't condense. So actually, the fact that the sun was weaker, well, it was a how do you say, a lifeline, a chance for the Earth. So there you go. The Earth is in what we poorly call the habitable zone, but that doesn't determine everything. You know, there's also a zone where you can condense an ocean. Overall, and this is important for what we'll say next, the Earth's climate is very stable. It has 3 possible stable states. If you vaporize the atmosphere, it stays in vapor form, at least today. That wasn't the case after the Earth formed, when the sun was bright enough for it to condense. If you start frozen, it stays frozen by reflecting radiation and staying cold. If you begin with liquid water, it remains liquid. You can move from one state to another. And, well, once the ocean is condensed, we still have a sun that is not very bright, so the Earth should be frozen and stay really frozen. So we need a greenhouse gas that is much more effective than today. The first hypothesis, the most logical one, which is based on what happens today, is that carbon dioxide was the main greenhouse gas. So at the beginning of Earth's history, we needed quite a bit more of it than we do today, yes. It had to be a major component of the atmosphere. Let's say there was 500 times more carbon dioxide than there is today. About 20% of 1 bar of atmospheric pressure to have a greenhouse effect, to have a sufficient greenhouse effect. So it's absolutely possible in terms of a CO2 reservoir. We actually have much more than that. You know, in carbonates, which are rocks that trap CO2, we have the equivalent of about 40 bars stored in the Earth's crust. So it's absolutely possible. But is that what happened? It's not obvious. Today we have a carbonate silicate cycle that keeps, I would say, the temperature above 0 degrees. But did this cycle that regulated Earth's temperature work that early in Earth's history? And for such high levels of CO2, it's hard to know for sure. Because when there's a lot of CO2 in the atmosphere, the oceans are acidic and carbonates aren't stable in acidic oceans. It's like cream in vinegar. So it doesn't work well, but that's the, let's say, historically standard scenario. That's it. As the solar luminosity increased, well, the carbon dioxide decreased, because there's this thermostat that regulates the two a little bit until we reach today's situation, and in the middle there's this oxygenation. There's another scenario where, well, this carbonate silicate cycle doesn't work well, and we need another greenhouse gas, which is methane. And methane, not like today, methane coming from the decomposition of matter, of living matter, but methane produced in a much more, how can I say this, independently of living things, well, by life, but starting from very simple elements, from carbon dioxide, from hydrogen, what we call methanogenesis. And which, well, in an atmosphere without oxygen, must have been more widespread than today. And in an atmosphere without oxygen, this methane could accumulate more easily, because methane and oxygen react together, destroying each other to form carbon dioxide and water. So we could have had methane, a very effective greenhouse gas, but you can't have too much of it. If there's more methane than CO2, it creates hazes, like on Titan, which reflect solar radiation and cool things down. So in that case, it's not good. That could have happened, meaning there could have been periods when the Earth was frozen. That could have happened. But well, it's still just a scenario. So we have two scenarios: one where carbon dioxide alone or with very small amounts of methane kept the Earth's climate above 0 degrees with liquid water, and that's been the case probably since very early on. Yes, that means that, well, we could have had so-called habitable conditions on Earth very, very quickly after its formation, as shown by zircons, for example. And then we have this scenario where, especially if we need a really hot Earth, if geological evidence led us to consider that the Earth could have been, at least at times, very hot, which is not at all a consensus. You know, we don't really have any reason to think that. At one point we thought that certain oxygen and silicon isotopes indicated that, but it's more likely the signature of locally high temperatures in hydrothermal systems. But if it really was very hot, and the carbonate cycle didn't maintain enough carbon dioxide in the atmosphere. It's possible that methane played a role, and if methane did play a role, then there must have been some fairly contradictory things happening in the atmosphere. At the time when life started to produce oxygen, because that methane doesn't coexist well with oxygen, and so the arrival of oxygen must have caused the methane levels to drop. And so the greenhouse effect of methane, and so by creating probably unstable climates or global glaciations, and we have global glaciations called the Huronian glaciation, which dates back to about 8 to 7 billion years ago, which could be attributed to this arrival of oxygen in a climate controlled by methane.
As fascinating as it is complex, yes.
And with very few constraints. So indeed, it's important to keep using the word scenario, as they may be contradicted by new scenarios. We may have forgotten some major atmospheric ingredients that played a role, but these are the main points of what we consider today.
I also wanted to bring you back a bit to the accumulation of oxygen. I find this event fascinating and a bit counterintuitive to think that between basically 3.5 and 2.5 billion years ago, the fact that life produces oxygen, which gradually accumulates in the atmosphere, eventually led to what we believe was an almost total glaciation, meaning the planet was entirely covered in ice. To realize that the consequences are on the scale of an entire world, on the scale of a planet. The activity of microbial life forms eventually, over a long period of time, completely transforms the atmosphere.
Many people, and I myself have often heard this comment, say that the Earth is too immense for us to be able to change anything about the climate. But the climate isn't the Earth, the climate is the atmosphere. It's this very thin layer that represents a tiny part of the Earth, and that we can change it. We've changed it over a few millennia, but we cause climate change by changing the amount of carbon dioxide. But carbon dioxide it's a minor component of the atmosphere. That has a strong greenhouse effect, even in small amounts. Here we're talking, when we go back to the oxygenation of the Earth, about an event that represents, so we went from no oxygen to today 20% oxygen in the atmosphere. So at the time of this oxygenation, we didn't go from 0 to 20. We went from a tiny, immeasurable amount with no effect at all on the environment to a molecule that, roughly speaking, controls the chemistry. And that suggests that there was maybe, 1 or 0.1% of the amount of oxygen today, which is already not bad, which already has consequences as well. So indeed, it changed the environment, so we can think about all the consequences it had for the living beings that were there. There is a very important one. As oxygen produced by photosynthesis accumulates, an ozone layer forms, that is, the O3 molecule starts to accumulate in the middle atmosphere and filters ultraviolet radiation, which is actually harmful. So you have to realize that these oxygen creators, they might be some kind of cyanobacteria, which started to create oxygen as a byproduct of oxygenic photosynthesis. That is, they take water, they break it apart with radiation, photons, light from the sun. They take the hydrogen from it, which they react with CO2, and with that they make organic matter, basically sugar, and that releases the oxygen that was in the water. And we do the exact opposite reaction. We take oxygen, we take sugar, we make them react, and we release some water and carbon dioxide, so we do the reverse reaction. But when life invented photosynthesis, it had this ability, it had invented it. It's not really the right word either, but evolution found this path that gave this huge advantage to need what? Water? Well, life needs water anyway, and it needs carbon dioxide. But there's carbon dioxide, there's some in the air, there's some dissolved in water. And light, well, that's where it gets a bit complicated, because at that time, light was dangerous. It was rich in ultraviolet radiation. So life, which today can do photosynthesis on the surface of the planet or in very little water, at that time probably had to do photosynthesis under quite a bit of water, or under sand, or under layers. It's also possible under layers of dead organic matter, under layers of dead cyanobacteria. That's actually something that still exists today, because you should know that when you get a sunburn, well, your skin heals itself, but when you're a microorganism and you get a sunburn, you die. So even today, cyanobacteria dislike sunlight and have their own strategies for coping. But when ozone accumulates, well, it helps. So all of a sudden, as the atmosphere becomes oxygenated, and then life was able to get closer to that light, which was becoming less and less dangerous. That's a positive aspect, but oxygen, it has several consequences. So there's already one. It's biological. It's the fact that it's an oxidant. It's little by little. We are living beings who use oxygen, which is a little round thing. But it's also oxygen that slowly kills us, right? That causes our slow combustion and that our body is made to protect itself from. We put up barriers everywhere. We let oxygen in where we need it, and we push it away from every other possible place in our body. You know, if you bite into an apple, the part you bit into will quickly turn brown, right? And that's oxidation. It happens very fast. So life wasn't born in an environment like that. It had to adapt to it and develop strategies. That's another thing that could have slowed down the progress of life a little bit, you know. And finally, there's the climate aspect. If the greenhouse gas was carbon dioxide and methane was a very minor gas, or even played no role at all in that case, adding oxygen to the atmosphere doesn't always have a clear effect. If the methane in the atmosphere was crucial, necessary to keep the temperature above zero, well, life, which released oxygen in there, caused the methane levels to drop. And this photosynthetic life, which needs water on the surface, since it needs liquid water at the same time as light, well, it's going to freeze in its own environment and put an end to, or at least greatly reduce its production, since it will shut off access to its metabolism. And so we can imagine that there were bursts of oxygen like that which caused glaciations. And then, as the cause of these glaciations, biological causes, disappeared, things started up again. And so we have a series of global glaciations called the Huronian glaciations, which could actually reflect this phenomenon. It's not certain at all, but it could reflect that. It's compatible because we have this extremely precise dating through a model. We think that when it shifts, when we shift from an atmosphere where oxygen dominates the chemistry, we have two completely different regimes for sulfur. In one case, when there's oxygen, it ends up forming sulfates. In the other case, it produces decomposed sulfur. Sulfur chains SS3 up to S8, and in the atmosphere, it produces SO2, which is kind of a competitor to ozone in photosynthesis. It creates some pretty interesting things. Let's say we have two types of isotopic fractionations. And after oxygenation, we have one type of isotopic fractionation, and before oxygenation, we have another type. And that's what really allows us to date this. But before this somewhat definitive transition, there is roughly overlapping with the Huronian glaciations. Some fluctuations in this isotopic signature, which could indicate that indeed there were some failed oxygenation events. After that, that's it. That's part of the problem, because it's not only in this way that the Earth became oxidized, it probably became oxidized in other ways too. If methane was an important atmospheric component, it probably became oxidized because methane carried hydrogen into the upper atmosphere, where it was lost. And so, but that if it's biology that produced that methane, which is possible in that case, yes, that's also the case. Biology is also another form, basically, of terraforming the Earth by microorganisms. So yeah, whether it's the methanogens or the ancestors of cyanobacteria that did oxygenic photosynthesis, and in many ways we had these terraformers of the Earth who paved the way for a world that is adapted to us. Of course, that's not really how it happened. We're rewriting history backwards. Of course, we adapt to the common conditions, but we wouldn't be here if we were different. Well, I don't know what sense that would make, but we really have an Earth transformed by living things. It's fascinating. So see you soon for the next episode.
That's too broad. There you go.
Because just to finish on that, well, living things, just the fact that life has transformed the planet, that's of course the main motivation for observing other planets, for observing exoplanets. And to think, well, maybe we'll come across another planet that has been transformed by living things in such a global, powerful way that it will be obvious. And so there you have it. This story of Earth, it's a great motivation for exploring exoplanets.
We'll devote a whole episode to this question.
Wonderful, gladly.